Let's talk about LLM Gateway pattern and why you should stop calling LLM providers directly from your backend services. So why do we need a gateway at all? Let me walk you through the core issues. When every microservice in your organization calls LLM providers independently, you end up with fragmented Quota consumption. There is no unified way to attribute cost to specific teams or features. You lose governance over who is using what, and debugging becomes pretty extremely difficult because logs are now scattered across dozens of services. Here's a scenario I have seen multiple times. One service has a bug, maybe an infinite retry loop or a prompt injection issue, and it burns through your entire shared deployment's token allocation in minutes. Without a gateway, you will have no visibility into this and you will get a bill which is pretty high, and you will start seeing rate limiting errors across unrelated services. The third issue is the provider lock-in. If you want to switch from one LLM provider to another or even add a fallback model, you have to touch every single microservice that makes the LLM calls. That is a significant engineering effort and a lot of risk. And finally, without centralized logging, cost attribution actually becomes pretty impossible. You cannot answer simple questions like which team spent the most amount of tokens last month or which feature is actually driving a lot of costs compared to rest of the features. Now, let's talk about how the LLM gateway patterns solve these problems by providing a single middleware layer across all your backend services and your LLM providers. Think of it as a traffic controller. Every LLM request flows through this gateway, which means authentication, rate limiting, logging, caching, and fallback logic all live in one place. Your application services become provider agnostic. They call your internal gateway endpoint, not the external LLM API directly. This separation of concerns is pretty powerful. Your downstream services can now focus purely on business logic. The gateway owns the complexity of retries, circuit breakers, and model routing. And when you need to migrate providers or add a fallback model, you update gateway configuration. You don't need to actually touch any of the consuming applications. This enables reduced downtime migrations via weighted routing and canary deployments, which is much safer than a big bang switch. Now let's walk through the four core components every LLM gateway should have. First is authentication. Every request should carry a valid API key or service token identifying which team, application, or user is making the call. The gateway validates credentials before any LLM resources are consumed. You also want scoped enforcement here, ensuring each caller can only use permitted models and token limits. And critically, in an enterprise context, you should implement PII redaction before prompts go upstream. Scanning for credit cards, social security numbers, or other sensitive data before it leaves your network is super important. Second is rate limiting. You typically implement this with fixed window or sliding window algorithms. The key here is that these operations should be atomic, usually via Lua scripts in Redis, to avoid race conditions under high concurrency. Your rate limiter should also return back pressure signals like retry after headers so clients can implement intelligent exponential backoff. Third is observability. So centralized logging captures prompts, completions, latencies, token counts, and error codes for every single call. This enables cost dashboards that aggregate usage by team, application, model, and time period. You also want latency metrics and prompt analytics to identify which templates work well and which queries consistently produce poor results. Now here's a common system design interview question, which they ask is, for example, design a system that prevents one team from consuming the entire company's token per minute allocation. There are several dimensions to this problem. First, you need real-time enforcement with sub-second latency at scale. Second, you should implement fair scheduling with priority classes. Typically P0 for interactive user-facing traffic, P1 for background tasks, and P2 for batch jobs. Production traffic should get reserved capacity while lower priority work uses overflow allocation. Third, you need to handle the consistency versus availability trade-off. If your Redis cluster goes down, do you fail open and allow all traffic and risking the quota cover overages, or do you actually fail closed and block all traffic and causing an outage? There is no universally correct answer, so it depends on your business requirements. And fourth is you should design for horizontal scaling, since a single rate limiter instance becomes both the bottleneck and also a single point of failure. Here's a rate limiter implementation that you can use in production. So the key insight is that we use a Lua script to make the entire operation atomic. The script runs inside a Redis as a single unit, so there are no race conditions between checking the quota and recording the consumption. Inside the Lua script, we first remove expired entries outside the sliding window. Then we iterate through the remaining entries and sum up the actual token values, not just count the number of requests. This is pretty important. If you use the zcard command, you get the count of requests, not the sum of the tokens consumed. This is a common mistake that makes your rate limiter enforces requests per minute instead of the tokens per minute. Then we check if adding the new tokens would exceed the limit. If so, we return a denial with the remaining capacity. If not, we add the new entry and set an expiration. The check_quota method simply calls this Lua script with the appropriate arguments and return a dictionary indicating whether the request is allowed or how much capacity remains. Now let me show you a fallback chain with the proper circuit breaker implementation. We define three states using an enum class. Close means normal operation where failure increments a counter. Open means all requests fail fast without hitting the provider. And half open means after a timeout, we allow only one probe request to test if the provider has recovered. In the constructor, we initialize each provider with a close state, a failure counter, and a timestamp for the last failure. We also create an async IO lock for thread safety in ASIC context. The get_state method handles the state transitions. If a circuit is open and enough time has passed since the last failure, we transition to half open to allow a test request. The execute method iterates through providers in priority order. For each provider, we acquire the lock and check its state. If the circuit is open, we skip to the next provider. Otherwise, we attempt to call the call with the timeout. Now, if the call succeeds, we reset to the failure counter and set the state back to closed. If it fails, we increment the failure counter and record the timestamp, and if failure exceeds the threshold, we set the state to the open. This pattern prevents the degraded provider from taking down your entire system. Traffic automatically routes to healthy alternatives. And now let me take you to step 3 to see how all of this fits together in a real-world architecture diagram. On screen now is the first architecture diagram showing an enterprise LLM gateway system. On the left, you have your client layer, web applications, mobile applications, internal services, and batch jobs. All of these send requests to the load balancer. The load balancer distributes traffic across multiple stateless gateway instances. This is key for horizontal scaling. You can add or remove gateway instances based on request volume without any state migration. Each request flows through the API gateway for initial validation, then to the auth service which validates the keys and attaches the team context, then to the rate limiter which enforces TPM quotas using Redis with atomic Lua scripts, and finally to the request router which handles caching, provider selection, and fallback logic. Now notice the data layer connections. The rate limiter talks to Redis for quota state. The request router talks to semantic cache for repeated queries. On the right, you have your LLM providers, primary, secondary, and fallback. The request router decides which provider to call based on the availability, cost, and routing rules. Now the second diagram shows a complete request lifecycle with quota enforcement. So a request comes in and the first check is authentication. Is the API key valid or not? If not, it returns a 401 unauthorized immediately, so no LLM resources are consumed. If auth passes, we extract the team identifier and check the semantic cache. This is an important ordering decision. We check cache before the quota. If we find a cache hit, we return immediately without touching the quota system or the LLM provider. This saves both Redis operations and LLM costs. If cache misses, then we check the quota. If this team, for example, within their token per minute allocation or not. If they are not, then we return a 429 rate limiter response with a retry after header so the client knows when to try again. If the quota is available, we call the LLM provider. On success, we update the token counter, log the request metrics, populate the semantic cache, and return the response. All requests, regardless of the outcome, emit structured logs for observability dashboards and cost attribution reporting. So to summarize what we covered today, the LLM Gateway pattern centralizes all your AI traffic through a single middleware layer. This gives you unified authentication, rate limiting, observability, and resilience. The code examples we covered earlier shows you how to implement atomic rate limiting with Lua scripts and proper circuit breakers with half open states. In the architecture diagrams, we covered how these components fit together in an enterprise system.